next talk is going to be given by Haridas from Oklahoma State University, titled Unveiling Global Dynamics of Monkeypox Through Deterministic and Data-Driven Models for Disease. Control and prediction.
Yeah. Thank you so much, everyone, for being here today. And I'm Haridas and I'm a final year PhD student in the Oklahoma State University. So today I'm going to discuss about the dynamics of the monkeypox and the possible modeling approach, considering the deterministic model as well as some statistical time series model, including some deep learning models. So monkeypox shortened is defined by the World Health Organization by Mpox. So I use Mpox here today. As you know, Mpox globally occurred outbreak in 2022, 2023 at some point from May 2022 to another May 2023. So I was curious how different modeling approach can be useful in analysis of the disease. So it's kind of a fun project led by myself, but and the monkeypox is a disease that is spread from infected animals to the person or the infected person to another infected person. I consider the univariate time series data from May 2022 to May 2023. And after doing a little bit analysis on the data, worldwide data, I found that the three continents, North America, South America, and Europe, are the leading reported cases. And some countries, and mostly USA, was also leading to the cases like the COVID-19. So it's 33,000 on that year. And I also consider Brazil in this analysis, right? So the most importantly here, I consider a data-driven approach, like a deterministic modeling approach and the data-driven models concurrently, which is mostly the important part of this talk. And the traditional compartmental model here, I consider kind of a vector-borne disease model concept here, considering the baseline contact rate, which is defined by C sub 0, and the proportion of contact between the human and non-human population, called the human and rodent. You could say high risk and low risk groups, like the same concept here. And the deep learning models I consider here are one-dimensional convolution neural network defined by CNN here. And LSTM is the long short-term memory. And by LSTM is the bidirectional long short-term memory and the hybrid CNN LSTM and CNN by LSTM. Note that during the COVID time, so people use this kind of model to analyze the COVID data. Even they consider single model for a single paper, but they did consider a lot of things, you know. But here I consider 8 different models together. And finally, I provided a short-term prediction using all this model, including deterministic and the deep learning models, with the statistical time series arima and exponential smoothing. So let me introduce the data set here. So the data were collected or accessed on June 3rd, 2023 for the training and testing purpose. And once the model ready for the prediction, I collected another data for the for comparison the prediction data with the model. So that is from the August 2023. So if you see the distribution of the monkeypox transmission, we see the 3 continents are reported cases were higher compared to the other continents. So you can see North America, South America, and Europe was the highest number of reported cases. On the other hand, Europe, Asia and the Africa has very lower reported cases. But if we convert this data into the incidence like 100,000 per 100,000, then we see still the North America, South Africa, and South America and Europe is the higher incidence per 100,000. But for the country-wise, I think Spain was the higher incidence per 100,000. But here I consider Brazil and USA in the analysis because their reported cases higher, perhaps the per 100,000 incidence cases was lower here. So now, if you see the time series of the daily incidence, it is very noisy. But people still sometimes use these daily cases in the modeling. But what I thought about since the CDC and mostly the researchers like to analyze in the weekly data. So I convert this daily incidence data into the epidemiological weekly data, which is from Saturday to Sunday. So with this epidemiological data, we can see the time series, which is very smooth compared to the daily incidence. And we convert this daily incidence by the normalization. We convert this weekly data into this. So our dynamics are same, but we convert into the normalization form. So note that I will use this normalized data in the deep learning algorithm because that helps to the modeling purpose. So the data partitioning here, I consider the 100% data from May 2022 to May 2023. So I use 60% of the training data and 10% for the validation. And rest 30% for the test. And this is only for the deep learning. For the statistical, I consider 70% of the training data and 30% of the tested data. And for the deterministic model, I use the 100% data set for the data fitting. But the deterministic model has a different approach for the data fitting. For example, window size, you can choose the window size similar to the deep learning. So that helps also to improve the data fitting. But I didn't consider here that case. And the methods or models, as I described earlier, is the deep learning model here, 5 deep learning models, 2 statistical time series, and 1 deterministic model. And we fit this deterministic model and estimate some parameters which are most sensitive to the model after doing the some analysis for the basic reproduction number. So we can evaluate the models at the end, and we can say this model might be the better model in the sense of the prediction. And we use 3 performance metrics like matrices, mean absolute error, root mean square error, and normalized root mean square error, right? But if we see how the data-driven models estimate the error or estimate the parameters. Here is the deal. So suppose this is the model, right? So you train the model on this data and you have an output, and you have the training label already, which is defined by Y. So you can define the loss function. For my case, I consider the least square function, least square error function. So you can use the optimizer that tells you, that gives you the signal, saying that your error is high, so improve your error or again. So it's go through this again and again. So it somehow stop with some conditions. So with all these methods, so the first thing I was interested with the analysis of the deterministic model or develop the model. So here I consider a baseline contact rate, which is defined by C sub 0. So if you see this matrix, these diagonal elements is the are the transmission rate inside that group, but the off-diagonal elements, they are connected the disease transmission from one group to the another group. So here we consider they are same. Perhaps I use the concept from some of the paper I use for this concept, of course. So using that, what I consider mainly here, the literature shows like there are two kinds of vaccination. So smallpox vaccination works for the monkeypox disease, that, and also there is those two vaccinations. So I thought like considering two classes here, right? And I also consider vaccination failure rate by tau. And also this is exactly kind of the concept of vector-borne disease. With that, I found the basic reproduction number and then use the sensitivity index formula here, the partial derivative of R0 with respect to parameter P times P over R0. So with that, I found like beta sub is, which is the transmission rate, and recruitment rate, beta sub and disease-induced death rate, mu sub and the vaccination failure rate. So these are the most sensitive parameters considering the locations and with different tau. So here the failure rate tau is 0, here is tau is this, right? So now the statistical time series is the standard model here, but the neural network model, I consider CNN. So the first thing you have to do, you have to train the data. So I have to define a sequence function that gives you the training label. Like there is a window layer, like you want to train 2 and predict 1 or 3 versus 1. So we have a training data that you can create by the sequence function. This is kind of the concept of window size. And then I use the CNN layers and then plot in the data and use the dense layer and then output layer. So every individual, these 3 deep learning models, only exceptional is I use the LSTM here and by LSTM. And then we use the CNN and then LSTM. So this is 2 of the hybrid deep learning model. So this is the parameters is available in the literature. So I use that mostly. And these are the population size and the fitted parameters, because the sensitivity index tells us beta sub is the important. So I use C0 and K1 important. So the result and discussion, the data fitting is here for 6 different locations. It's okay, but not perfect for this location. And here it shows that the vaccination rate is important, because when the vaccination rate increases, the epidemic size percentage decreases, which is very natural in the deterministic model. And also it tells us when the vaccination increases, the plot in the curve, and also the cumulative cases. And this is also important because this is a two-dimensional color maps that tells us that if we consider C0 and K1 from this blue region, then there is no chance of epidemic. And the criteria of this binary map is if the maximum of the infected cases throughout the domain, like time domain is bigger than 2, then that is the epidemic, right? So this is the same concept, came from my another paper in SIAM journal.
You had a slide or two.
Yeah, I'll finish. So, and this is the training from the data-driven modeling, which captured the dynamics properly. But let's closely observe the test data. So this is the small window, 40 to 56 weeks. And if you see the trend almost same, except the statistical time series kind of upward trend, but the other model captured the dynamics. And it looks like the disease is in the die-out situation that captured by the model. And the prediction shows some models, the dynamics is in the upward, but hybrid deep learning model gave us a better prediction in the die-out situation, which was consistent with the actual data. And the main takeaways is I consider different modeling approach and use the prediction and found that deep learning hybrid models perform better as well as a deterministic model. So I think that's all, but the paper, this presentation is a part of the papers published recently in Frontiers in Epidemiology. And I acknowledge, of course, many professors because I share my idea with different people. And when they said you are in a good direction, then I got, more strength to write the paper and finally publish. And I also thank to the organizer here and the SIAM community to give me the financial support for this presentation. Thank you so much.
Any questions of anything very much?
Yes, sir.
Sort of interesting that how far into the future you project with these models, right? Especially with these machine learning models, because they're just trying to mimic the time series, right? There's no mechanics built into it. So did you try for different the projections into different times into the future, like 2 weeks, 4 weeks, 6 weeks, something?
Yeah, so that's a good question. So as you know, deterministic model cannot predict. Of course, deterministic model can predict for a long time because you have the fitted parameters and you can run the simulation for a long time, right? So I cannot predict the deterministic model for many long time, like 8 months or 12 months or, so since I was comparing the different models together, that's why I run the prediction, the deep learning prediction for 8 weeks. But of course, I can run many longer. And because I consider deterministic model for 8 weeks, that's why I also consider 8 weeks for the deep learning model. Yes.
So did the machine learning model always perform better no matter how far into for shorter, my sense would have been that for shorter time, they probably do better, but as you go towards longer time.
Exactly, because, LSTM is the long short-term memory. So it performs well in the shorter term. So for the long term, maybe it may not perform well. So that's the, yeah.
Well, if there are any other questions, I will have to wait for an intermission period. Thank you very much, Haridas.
Thank you so much.